Ο κύριος Μαχμούντ Φουάντ είναι καθηγητής και τέος πρόεδρος του Τμήματος Μηχανολόγων Ηλεκτρικής Ενέργειας και διευθυντής του Εργαστηρίου Ενέργειας σε κτίρια του Πανεπιστημίου του Καΐρου. Συνεργάζεται με τα πανεπιστήμια Κάρλετον του Καναδά, Μπέρκλι της Καλιφόρνια και το Αμερικάνικο Πανεπιστήμιο του Καΐρου. Έχει εργαστεί ως τεχνικός σύμβουλος σε πολλά έργα και εταιρείες, κυρίως σε τομείς της μηχανικής των κτηρίων. Είναι μέλος του Αιγυπτιακού και Αραβικού Κώδικα Πρακτικής των Μηχανολογικών Συστημάτων για τα κτίρια. Υπηρέτησε την Άσρα σε πολλές θέσεις και διατέλεσε πρόεδρος του Αιγυπτιακού Παραρτήματος. Mr. Fouad.
Well, thank you very much. I hope a lecture that would start after 5 p.m. wouldn't be that bad, but I hope the subject might be interesting. We'll talk today about two very important tools that are used within the design stage or even after that. It's a continuous process. We'll talk about two particular tools that are mostly used, the energy modeling and the CFD, and their importance in the building industry. So the talk would perhaps be composed of two parts, one regarding the energy modeling of a building, and the second would be the computational fluid dynamics of CFD simulation of a building. Then we'll try to deduce some conclusions for that. As for the first part, as we talk about energy modeling for buildings, we'll perhaps introduce a subject, then we'll go for energy modeling applications and energy inputs, creation of the baseline building model. This is very important in order to be able to compare the results of a particular design of a building with the standards. We have to create the baseline building model. Then the steps of the building energy modeling, and we finish this part by giving an example building that we carried out this analysis and see some sample of the results of the energy modeling of such a building. If we try to define building energy modeling, we'd perhaps refer to this very simple definition. It's the use of computer-based tools to simulate the annual energy use of a building. So it is a simulation of the performance of the building throughout the year, hour by hour. It is also used to assess the energy use of the building and to assess it whether it complies with the standards or not. In addition, this tool is very important to quantify the savings that is contributed to particular design. This is very important because we are able, if we are doing this early enough in the design process, we are able to change the design and carry out the same analysis, energy modeling, and compare the design changes, how effective they are, and whether we can gain out of these design changes. It also enabled the design team to make priorities of the investments in the strategies in energy use, whether any change that might be suggested would be useful in terms of how much useful would that be, and is it worth the investment or not from economical point of view. So actually it is, from this very simple introduction, it could be a very important tool in evaluating the performance of the building. The applications of such important tool would be a building commissioning process, and we just heard a very great lecture, although, and this is most of it actually from what is written. Next time I'll learn some Greek somehow and I'll put the whole lecture perhaps. It was a great lecture, and I guess building commissioning, as you have seen, is a continuous process. And we also claim that energy modeling is a continuous process. It's not related to a particular stage of the work. High performance buildings, obviously, if we intend for our building to be of a high performance, we need to apply this tool into it. Healthcare facilities, building operation and maintenance, as we've just seen from Vasile's lecture, actually, that it is a continuous process, not just a design process. It's a process that may be continued for the life of the building. Now, if we think in this brief introduction, what are the data required as an input to this procedure, would talk mainly about the location, related to the climate data and the interior conditions, set points. All of this are related to the particular location of the building and its use. The envelope also is very important, and we have seen today so many presentations related to the envelope, so many presentations related to the material that might be used. So the area, orientation, and solar properties, the U values, and so on, and materials used in the facades are very important. The solar heat gain, the visible light, and so on. All of these parameters related to the envelope of the building. Mass of the building components is also important, as you know that building material are used as a store of energy. And we need to understand the storing characteristics of this building material. Infiltration rate is also very important. If we look at the internal gains, we look at lighting, we look at electrical loads, we look at sensible and latent loads within the building. After collecting this data, we have to thoroughly understand the schedules according to which all of these systems work. The lighting schedule, whether it operates before the people get into the building or after the people get in a building, whether it operates only in the evening or is it for the whole day, what are the allowances that are allowed from the building windows and so on for the day lighting harvesting in the building. Electric load schedule, occupancy schedule, and so on. Then we look for the systems. Heating system, cooling system, ventilation system, fan and pumps, input, and so on. We look at all of these systems, then we are happy with the data that we are prepared to get into the energy modeling procedure. Now, according to ASHRAE standard 90.1, we have to create the baseline model. The baseline model is the same building under consideration, but within a particular orientations in order to compare this baseline model with any design modifications that we could make and accordingly gain points in any of the evaluating schemes and gain some of these points. According to ASHRAE standard, we have to do this 4 times and take the average of the 4 times that we carry this on the building. Of course, the building has to be modeled in its original direction. Then we turn that 90 degrees and 180 degrees to 170 degrees and take the average of these 4 orientations. At this point, we have reached the baseline building that we can use for comparison with any design improvement that we introduce. All the data that are introduced to this building at this point are from the standard. So we have to introduce the values that the standard necessitates. And then we look at our design and compare whether we improved upon the standard or are we less than the standard. Obviously, the standard represents the minimum value that, or the minimum energy performance that's expected from this building. But we hope that we can get higher performance than the minimum that the standard requires. Now, as we created the baseline of the building, now we go for the further steps. We divide the building into different spaces, and we make simulation on the individual spaces. Then we make simulation of the individual systems, whether the systems are HVAC systems. That's obviously the main consumer of energy in a building, or in non-HVAC systems. We have to model all the systems that are included in the building. As we do that and we carry out the design procedure, we would be able to get some results, and then this result, we have to analyze the results and conclude some remarks that are related to the design, that whether this design is suitable from energy point of view, or do we need to introduce some modification at this point. So to sum up these steps, I've just put this simple slide that would perhaps help younger generation when they have this presentation later on at their convenient time, what to do in order to model, do some energy modeling for a building, to define the problem, to gather the data, make the simulation of the building, and then defining the spaces, creating the HVAC systems, creating the non-HVAC systems. A none should be introduced here, creating the HVAC plant as well as a system, and simulating utility rates. This is very important, and this is different from one country to another. In some countries, like ours, for instance, I come from Egypt, it is a flat rate. In some other countries, it's not a flat rate. People are encouraged to use energy in the non-peak situation, and this is obvious, and discouraged to use energy during the peak time. So obviously, you won't use the things that you can schedule in your time, like using the washing machine at home and something. You can postpone that to the non-peak hours so that you get use of the lower rates. And in this way, the governments would not be required to install huge installments for power unnecessarily. They have to do that on a necessary basis. Then you produce the results and you analyze the results and then you conclude. Let's go for an example. I just picked up, I choose this building as an example. This is a building that we designed in the Middle East. This is the shape of a building. It does not look like a normal building. It is, in fact, and judging from the area, as you can see, this is a main airport terminal building. Just because I didn't put the name of the airport, because I had to ask the owner, and I didn't actually before coming down here. So I just put the numbers and figures of the work that I have done, and my team has done as well. But you can see how huge is a building. Then, after having the building, we started to make the input data for the building, including the site climate in the particular city where this building was located, construction materials used. We have seen today in so many presentations the importance of these materials, building size, layout, and so on. We started to model the internal loads of the building, expected loads. That was early enough in the design stage. Then we introduced the data for HVAC systems and the system and the plant, and for the non-HVAC as well. Domestic water was included, and of course, we introduced the utility rate. In fact, the utility rate was a flat rate as well, just the same way as it is in Egypt. Now, the climate data for this particular building, as you may see, is very moderate compared to the rest of the Middle Eastern cities. And that was for a reason, because this building was actually placed in a city, very elevated city than the rest of the country. So actually the weather was very moderate compared to what's expected in this area, from the Gulf area in the Middle East. Of course, we modeled also all the different data. We collected all data for total heat gain, for instance, for all directions, as you can see, and for all hours of the day. And of course, that is repeated for the hottest day of the year. Also, my team and myself, we were very concerned about the daily solar radiation statistics, and we collected that for this particular building for the whole year, whether it is a maximum or an average or a minimum. And then we after that, we prepared ourselves to get some results, and we started getting the results. I'm only presenting here, I'm sorry. I'm only presenting here some samples of the results, of course. The results are huge in terms of size, and in fact, the report was somewhere larger than 500 pages of results. So of course, there is no need and no room for that to present that today. But I just got some sample of the results. What do we expect to get out of this procedure? For the plant, for instance, we started to model the plant and what we get throughout the year, the energy consumption of the plant throughout the year, and this model, whether in the tabular form as table or in a graphic form, you can put it the way you like. Then you can carry out the same procedure on a daily basis for the plant here, for instance. And a daily basis here, of course, we concentrate on the high demand, but we also compare that with other days of the year, not only at the peak of the consumption of the building. Same thing, we go for details of the systems. We can simulate the primary chilled water. The system in this building was using both primary pumping and secondary pumping systems. So you can model the primary chilled water pumping as well as the secondary one. You can do it throughout the year and also day by day. So for instance, this is the consumption of the secondary pumps of the system on every day in the month of July, which happened to be in this particular location the highest months of consumption where most heat is expected in this particular location where we carried out this analysis for that particular building. Also, you may go for other details like the annual coil loads, whether it is a cooling coil or a heating coil. You can do the analysis the way you like, whether it is a total consumption, total load, or is it a load per square feet, and so on, so that you can make your comparisons with the baseline building, as we said, in order to compare it with ASHRAE 90.1 standard. That's the standard that we've used in the comparison. Annual energy consumption of the system components. As you see, you can go throughout all components of that consume energy in the building, from system air fans, cooling, heating, pumps, heat rejection fans, HVAC, subtotal. All of these would represent the HVAC. Now, the other non-HVAC could be the lighting, could be the electric equipment, could be miscellaneous electric, could be miscellaneous fuel, and so on. You can carry out the whole thing for the whole systems included in the building, and you group them into two main groups, HVAC and non-HVAC. Then you may add this up. This is the overall consumption of the energy in a particular building, and this is the example of the building that we are giving. That was the type of consumption that we had. Now, you can also carry out this analysis month by month, and you can actually carry it out day by day. This table, for instance, presents the monthly consumption of the building throughout the year, starting from the month of January till December in the year. And you can also do all types of analysis that you would like from the building to see the percentages of the consumption of every particular system included. And for this particular building that we are presenting here as an example, that was the percentages of the consumption of energy in the whole building. This table and graph present the monthly HVAC energy use and the monthly non-HVAC energy use, month by month, and then you add them together and you get the total and overall consumption of the energy of the building also throughout the year, month by month. So in that regard, actually, it's just I wanted to present some example of results to give you a flavor of what do we expect, but of course I did not put too many results here, otherwise we'll end up, you will hate me, it's after 5 o'clock, so I don't want that to happen. All right. Now, being that brief, let's go for the next part of the presentation, which is application of the other tool that we intended to present. Energy modeling was our first tool. Now, the computational fluid mechanics or dynamics, CFD, simulation for buildings, that's the second tool that we consider very important for the building. Again, it's a continuous process, not only for the design stage, but also for the lifetime of the building. Now let's introduce just a brief of what are we going to introduce here, making some introduction of the CFD steps, advantages of CFD, just a very brief consideration for the grid, what to do, and then gathering data. And again, we're going to apply that to another building. In this case, in fact, this building is in Egypt, and we see what do we get out of it. Now, in doing CFD analysis, what you do actually is you discretize the building, the geometry, you discretize it into small pieces in a grid, you create a mesh grid, and you actually have to think about the subdomains that you are creating, and this takes some experience actually in order to do that in the right way. Then you have to think about the boundary conditions and what are the boundary conditions involved in this particular application. And in the example that we are going to drive in a few minutes, we'll see what type of boundary conditions did we simulate. Then you, of course, take the conservation equations. Conservation equations, as you're all familiar with, is just a term that combines all the equations that govern the movement of a fluid, the air in our case here, in a building. Conservation of momentum, conservation of mass, conservation of energy. Just one word to connect them all together and make it easier for us to represent them. You apply that at each mesh element. You don't apply, and that's the beauty of computing here, because you are using computer power instead of using analysis that people in the past used to do, and of course they would not be able to do this type of analysis without the existence of computers. Coupled equations are solved so by numerical analysis here that you overcome the problems of being coupled, and then you obtain the solution data. Of course, it is reasonably rather than responsibility here. I'll correct this word perhaps. CFD provides reasonably accurate predictions of performance, so you know the performance in advance before actually you install the system. This is a beauty. And you also, that's a beauty again, are able to evaluate and to predict any the effect of any change that you make to the design. You don't have to be content with one design. You can make changes in the design and evaluate it very quickly and see whether these changes are feasible or not, whether this would be any helpful in what you are doing. You are also, you can obtain detailed information about the system parameters, so you can do, in other words, parametric study, and you see which parameter would affect your design the most. Then you make a decision, you make design decision for yourself, and you see, well, this is the thing that I'll do. Obviously, design alternatives here are obvious. Then you compare them and you sort of make design decisions.
Mr.
Now,
FOUAD, you have 5 more minutes.
5 more minutes, my God.
Yeah.
That was, okay. And then I'll have the freedom after that. I'll be free.
If there aren't any questions, you may continue, of course.
Well, I'll try to finish. I'll just give some brief results and I'll let everybody free after that. When we talk about grids, we have to think about the gradients. This is where the experience comes in. You have to expect regions of high gradient. What I mean by high gradients here is that areas where the velocity change very much, areas where some other parameter changes very much, not only velocity, of course, only other parameters. So that's kind of experience that you develop by the time as you are working on this. And then you carry out a grid sensitivity. You don't have to make too much nodes in the grid. And of course, you cannot depend on the results if you carry too little of the mesh points. So you have to make the compromise and make the grid sensitivity, and then you conclude for yourself, after this number of mesh nodes, I don't need any more numbers, and my results will be accurate at this point. This is just two quick comments here. Now let's go for the example building. The example building here, as I said, was in Egypt. It's an underground garage in a very luxurious residential compound that has many low-rise buildings, and the garage is 2 floors as basements underneath of this group of buildings. What we carried out as type of analysis for this particular building was a normal ventilation case and also the emergency smoke exhaust case. This is the AutoCAD drawing of one of the basements, one of the 2 basements in the garage. And just to give you a flavor of the size of this particular garage, the area per floor was 7,000 square meters. And this is the CFD drawing of this particular garage. This garage is used for parking as well as for storage for the apartments that are in this luxurious residential buildings. So it actually has, the problem is it also introduces some obstructions in the way of ventilation in this particular garage. It's not only cars, but also some storage places that are introduced in this particular building. This is a schematic drawing that shows the locations of the fans as well as the locations of the air inlets and exit in this particular basement garage. And it also shows the entrance and the exit areas of the different cars getting into this basement. Now, we simulated the different fans, but before we simulate it, you have to collect data for the fans, whether they are exhaust fans or supply fans and so on, and actually, or jet fans, in our case here, that was the case. And also, whether these fans are single speed fans, double speed fans, variable speed fans, and so on. You have to do all of this analysis, and because that would, in our case here, create your boundary conditions. The boundary conditions at entrance to the fans, at exit of the different fans. In this way, you will be able to make the simulation in the right way. So the locations of the fan, and also the scenario of operations, because not all of these fans are intended to be used in the normal ventilation case. The normal ventilation case, you are only operating the exhaust fans and the supply fans at particular speeds. But in the emergency case of fire and smoke resulting from fire that we hope that, God forbid, this case, but as designers, we have to do this analysis. The jet fans would operate, and some fans would operate at a much higher speed than its normal ventilation case. So this is referred to as the scenario of operation of the different fans, and we have to simulate that. And of course, the areas of inlet and outlet of the air have also to be simulated. Just let's have a look at some of these results, sample results of this building that we carried the analysis for in Cairo. In a normal ventilation case, of course, that's the ordinary case. You are interested in knowing the values and the distribution of the carbon monoxide that would result from the incomplete combustion of cars that start within the garage. As you know, CO is a very risky and dangerous gas that people are only can exist in some concentrations of CO for a particular period of time. So you have to think about that and apply all the analysis and all the criteria of the highest value of CO. Also, the velocity is very important because, as I said, in this particular application, we had other problems other than the cars. We had these storage areas that were placed in the garage to help the apartments not using a store within the apartments themselves. Now, in the second scenario where we modeled the smoke exhaust, we have also to be concerned about CO. Now, CO is of a more concern because that's a typical product of the combustion of a car. How many cars would go into fire? We had to go for many statistical analysis, and we made conclusions in that in order to be able to make the right model. Then CO distribution, temperature, and soot concentration is also very important because even people who are escaping from the garage during the exhaust, the smoke exhaust time, they have to go out and now the visibility is the most important parameter because people may get into panic if they don't see. So the visibility is of an extremely important. Now these are the different levels, breathing levels of adults, of children, and so on. I just have to run because now I'm getting the warning. These are some kind of results that we actually got from the simulation. Of course, as we get into the red region, this is the most dangerous, a lot of concentration of CO. The blue region here is acceptable region. And we can compare that, we can compare different designs, different scenarios of operation of fans with this and conclude for ourselves what is the operating scenario that we would accept. Velocity distribution also, we have to see the stagnant areas and of course, we are scared the most from these stagnant areas and we need the air to move in that situation. Now, as the smoke exhaust, also that was modeled in our case, and these are the results for the CO concentration or the carbon monoxide concentration, and same thing happened for the temperature distribution. This is a close-up, actually this is another drawing, a close-up to the position where the car in fire is, of course, at this position. We expect a very high value of temperature. Then, as you can see from the other drawing, I'm sorry that the two drawings just came together, close together. They should be separated, actually. You see that most of the garage is safe in that regard, according to this study. Also, the velocity distribution is very important. The velocities, of course, are higher, very close to the car and fire because it's the velocity of the smoke that is generated. And obviously, that depends on the level that you are modeling your results in, whether it is a breathing model of people or children or adults, or it is at the smoke layer level. Visibility is the most important of them all, and as you can see with the particular design that was employed at the end, that was not the original design, but as we went into the right design, as you can see, visibility was occurred, and visibility is measured mostly in 10 meters, and don't look at me this way again. I'm scared now. But let me finish, because I respect actually that we got in time for the whole day. I thank you very much. We have two very important tools in hand, and I think this is the future of all building design. Thank you very much. Thank you.
Thank you very much, Mr. FOUAD.